Welcome to the next video in a course in real analysis. This is lesson 5.2. We will be doing exercises regarding the absolute value and inequalities. So the exercises that we will see will generally be about inequalities that look roughly like that and things having to do with the absolute value. So the first exercise, we're going to take an ordered field and two elements, A and B, in this ordered field, and we will show that if this inequality, A precedes B plus epsilon for every positive epsilon, if that is true, then A precedes B, right? The same is true if we replace the precedes with a preseek, okay? And then we will generalize this result to sort of the most, or one of the most general ways that that we could express this basic idea. And I guess I should note, as I'm explaining this, this is going to be quite important. We are going to use especially this generalized version of it all the time in this in the coming lessons. So anyway, this is going to be like a strategy or a technique for showing a lot of inequalities. So anyway, here's the general version. If we take any two elements, A and B, and if we take two positive elements, C and D, then if these things all satisfy the following property, that whenever epsilon is taken between 0 and D, I don't know why I wrote delta, that's a D, anyway, then we have this inequality, right? So if this is true, right, whenever epsilon is in this range, then this inequality follows. If that is true, then it must be that A precedes B. Next exercise showed that if x is greater than 1, then 1 over x is less than 1, and somewhat vice versa. In the next one, we first define the notion of the absolute value of an element in an ordered field. So if A is an element of the field, and if it is non-negative, then the absolute value of A is equal to just A. If, on the other hand, A is not non-negative, which is to say if A is negative, then the absolute value of A is negative A. So there's the definition. That is the definition of the absolute value of some element A in an ordered field. Now, let's take any two elements, A and B, from our ordered field, and all of the following facts, and I think there's one more on the next page. So all of these things follow from being in an ordered field. And that's the last exercise, so in a minute I'll start showing my solutions. Okay, for this first problem, then we will assume that for every choice of a positive epsilon, the inequality A precedes B plus epsilon holds. And we are now going to try to show that A precedes B. Well, how are we going to do it? I guess if we have no other thoughts about how to approach this, then maybe we'll just assume B precedes A for contradiction. Now, from here, where do we go? Well, often it's a good idea if we're saying that A is bigger than B, then, often we'll be just kind of interested in or make use of this distance between the two of them. And so in particular, right, we'll say that epsilon is A minus B. That is a positive quantity because we're assuming that A is bigger than B. And then because this gets us this positive quantity, right, that's why a lot of the things that we state have to do with these positive quantities is because often these positive quantities are some kind of a distance, but in any case, so now we know that A precedes b plus epsilon because, after all, epsilon is a positive quantity, and this is a property that we assumed for this part of the proof, or this statement. But when you expand out b plus epsilon, I mean, after all, we are doing b plus a minus b. Well, the b's cancel, the a remains, so this is equal to a. Now, we have that a precedes a, and that is a contradiction, so this part of the proof is done. But when we move on to the next part of the proof, we're replacing precede with preseek, and you can tell that if we made the same choice of epsilon here, that it would no longer work, right? We would get a preseek a, and there would be no contradiction that follows from that. Well, often, when you're doing a proof like this, and by the way, I guess I'll just go ahead and mention we're, again, going to assume B precedes A for contradiction. That part's not going to change. But we're going to pick a different epsilon. And a lot of times, if an epsilon is so close to working, right, because we have A preseeks A, and that's not quite what we want. But it almost feels like it's so close, right? Saying A precedes A is so close to A precedes A. There's just a small perturb it a little bit in one direction or the other. Anyway, some intuition like that generally should tell you to set your epsilon just a bit smaller, right? Typically, if you have this free choice of epsilon, then choosing a smaller epsilon, if you can, in some principled way, is often a good idea. So in this particular case, we're going to do the same choice that worked before, but this time we'll divide by 2 just to get something strictly smaller than what we had last time. Let's see where this goes. If we do a similar trick to last time, then we say that because epsilon here is clearly positive, then A precedes B plus epsilon. When you expand that, right, when you say, well, epsilon is this thing, so when you take this thing and add B, okay, you're going to get common denominator, so you're going to multiply B top and bottom by 2, and then you're going to add these fractions together, basically, and then the 2b and the minus b are going to combine and turn into just a plus b. Anyway, long story short, you can work this out on your own. But that's the result of doing b plus epsilon. But from here, we would like to get some kind of nice relationship from this inequality. We would like to get some nice relationship between a and b that maybe will lead to a contradiction. Well, with a on the left and a plus b over 2 on the right, we can multiply the 2 to the other side. So on the left side, we've got 2a. On the right side, we only have a plus b. Subtract a, and you get this. A precedes b. But remember that we assumed for contradiction that b precedes a, and these two are in contradiction, and so that finishes that part of the proof. And now for the hardest part, to generalize this even further, let's assume that a and b are any numbers, c and d are positive, epsilon chosen between, whenever epsilon is chosen between 0 and d, then we get this inequality. Okay, we would like to show, yet again, that a precedes b. For contradiction, assume that b precedes a, just as before. Now, this is a very important technique, and we will see a lot more of this in future videos. But the idea is, well, I need my epsilon to be chosen between 0 and d, but also I want my epsilon to kind of cancel out the c, so I want the c in the denominator, and I also want that once the c has been canceled, then what's left over is a minus b over 2. So there's a lot of things that I would like to satisfy all at the same time. Well, some of them are relatively easy to make happen. I mean, putting c in the denominator is no problem, and having everything that's left over after the cancellation, that being a minus b over 2, that's no problem either. But how do we also make sure that it is less than D while all the other things are also true? Well, that's why we take the minimum, right? So we put D here, we put the other quantity here, and by taking the minimum of these two, then we are guaranteed that both inequalities, right? This inequality is going to be satisfied because we're taking the minimum. So epsilon is going to be smaller than D because it's the least of these elements. Okay, maybe to get the inequality strict, we need that divide by 2, but that's going to happen. So basically, by having D in the set, then we and ultimately we're dividing by 2, then we know that we're going to get an epsilon that is smaller than D, and then I can leverage, or I know that I satisfy this condition, and so I get to use this right here. Also, by having this in the minimum set, then at this point I can argue that that epsilon is smaller than this quantity, right? And so, so basically by putting these two things in the minimum, I get both conditions, or like both of the things that I would like to have happen, I get them both at the same time. And this is a common technique, right? When I have multiple conditions to satisfy, generally involving an epsilon that needs to be small in order to work, then we typically take the minimum for all of the conditions that we have to satisfy. So, based on the construction of epsilon in the previous slide, we know that epsilon is between 0 and D. We can also show this. Oh, that should be an epsilon. So C times epsilon. By changing out epsilon for something that is bigger, we get C times that, and canceling the C's, we get that. So altogether, what this tells us is that because this condition was satisfied by epsilon, this tells us that by the assumption of this problem, that A precedes B plus C epsilon. Because of what we have here about C epsilon, we know that that precedes B plus A minus B over 2. And so, all together, with all of that chained together, we obtain this result. And yet again, right from here, we can multiply by 2, subtract A, and obtain that A precedes B. So that concludes the proof. So in this slide, I'm just kind of elaborating. I am sort of reiterating a lot of what I said, that basically we had two conditions, right? We needed this condition satisfied. We also needed this condition satisfied so that some of the algebra later on would all work out. And that's the same thing as this. So anyway, what you can mostly think of this as is two conditions, right? We needed epsilon to be smaller than D and also smaller than this quantity. And so again, right, that it is going to be a commonplace that when we need multiple conditions with an inequality, both of them indicating epsilon should be small, then in any situation like that, we're going to take epsilon to be the minimum of some two things, perhaps further divided by 2 if we need the inequality to be strict. Now, there will also be situations coming up frequently when we don't want some quantity to be small, like we don't want epsilon to be small. Sometimes, often it's a natural number for reasons that we'll see later on, that we would like to be large, right? So we might have two conditions where we want to pick a natural number n, subject to the condition that it is bigger than this other natural number, n1, right? So for some reason, somehow, we're going to have this n1, and we want to pick an n that is bigger. But also we're going to have an n2, and we would also like n to be bigger than n2 as well at the same time. And so when we want n to be big, and we have these two conditions that we must meet simultaneously, in a situation like that, we typically take the max in order for both conditions to be satisfied simultaneously. And of course, it would be natural to wonder that, whether or not there would be other conditions where, like, sometimes we want it to be bigger than this and smaller than that, and perhaps that will happen. But they, uh, don't worry too much about that, because it happens so often that we either want epsilon to be small because, like, it needs to be smaller than multiple things for whatever reason, and often we want some n to be big. Those things come up so often that you just want to be in the habit of thinking about taking the minimum or the maximum. It's a commonplace, and that's all you need to worry about for right now. So don't worry about other possibilities and how you might handle those. If they're more complicated, then maybe there's some more complicated strategy, and we'll address that when we get there. But for now, I just want to make sure that you have this tool in your toolkit, because it will come up so often, specifically in the case when we want something small, or in the case where we want something big. Okay, to show that if x is greater than 1, then the reciprocal is less than 1. Well, it just comes from multiplying both sides by the reciprocal. So really hardly anything to show there. And basically, the same story is true here, right? And we know the reciprocal exists because it is greater than 0, so not equal to 0. So you multiply throughout by the reciprocal, and we know that it preserves the order of the inequality. So all of this is very straightforward. Okay, for the absolute value, we will prove parts 1, 2, 3, 4, 5, but actually I think I'm going to start from proving property number 2, because if I can prove property number 2, then property number 1, I could start by writing absolute negative a as negative 1 times a. Then there's an a, there's a b, so I can split up the absolute value. Although this would be negative 1 and this would be a, so okay. But then absolute value negative 1 we know directly, because that is negative. So we're in this case, and so this turns into negative 1 times absolute a, and that's the same as 1 times absolute a, and that's the same as absolute a. So anyway, so I've basically given the solution for 1 if we can find the proof for 2. So let's actually just start from the proof of 2. And by the way, there will be a similar easy proof for 4 if we can first prove 2. So that's where we start our focus. For property number 2, there are 4 cases, and they are about, are A and B both non-negative? Or is A negative, B non-negative? Or is it the other way around? Or are they both negative? So those are our 4 cases. In the first case, where everything is non-negative, then the equation to demonstrate is simply, it simply reduces to AB equals AB. Why? Because AB is going to be a non-negative number, because we know that it's a product of 2 non-negatives, so it's going to be non-negative. And so then the absolute value of AB is going to just be AB by definition of the absolute value. So the left-hand side just turns into AB. Okay, what about the right-hand side? Well, absolute A is just going to turn into A. Absolute B is just going to turn into B. So we just get this trivial equation immediately. And so this case is done. So next, we'll move on to assume that A is negative and B is non-negative. Now, in this case, we know that when you take A times B, then that is going to be a non-positive number, right? A strictly negative times a non-negative is going to get you a non-positive. Okay, so since that's non-positive, then we can say that absolute AB is going to be negative AB. Certainly that's clear if it's strictly negative, right? Then we would just know immediately from the definition of the absolute value that this is what it would be. But also in the case where it's equal to 0, well, if it's equal to 0, then this would just be 0, this would be 0, and so there you have it, right? So whether it's 0 or whether it's strictly negative, in both cases, we know that this follows. Okay, now absolute A in this, under these assumptions, would be negative A, and absolute B would just be regular B. So if we compute this thing piece by piece, we get negative AB. Well, okay, then what we found was that from here, absolute AB is negative AB. And then from here, we know that that's the same thing as absolute A, absolute B. And this, right, the equation of the far left and the far right, is exactly what we were trying to demonstrate. In the third case, well, that is essentially just swapping the roles of A and B, so kind of without loss of generality, the proof that we gave here also applies there. So the only thing left to show is the fourth case, and in the fourth case, where both of them are strictly negative, then their product is strictly positive, and in that case, we know that absolute AB is just equal to AB. Also, we know that absolute A is negative A, absolute B is negative B, and then when we compute this thing piece by piece, we get negative A times negative B. That then simplifies to AB. Since both sides, right, since absolute AB was just AB, and also this thing here also is AB, then they're equal, right? That concludes the proof there. Okay, as we already outlined for right now that we have that result from part 2, we can use it to quickly get a proof for part 1. Also, let's look at, I think this was part 4. And in part 4, we want to show that absolute A minus B is equal to absolute B minus A. Well, what we can do is factor out a negative from inside those absolute values, and then use what we just showed up here, that if you have a negative inside the absolute values, then you can just drop the negative. And so that is the demonstration of part 4. Okay, for the demonstration in part 3, I don't think we can just deduce it quickly from part 2, so let's consider some cases. And remember that what we're trying to show is this inequality, or chain of inequalities. So again, we're going to consider cases, right? Case 1, A is non-negative. In that case, its absolute value is just A. And it is easy to demonstrate in this case. This is merely by reflexivity, but then here we know that like this is less than or equal to 0. This is greater than or equal to 0 under this assumption. So we get this chain of inequalities, and then if we kind of put the absolute value back in, we get the desired result. So there's the proof under the assumption that A is non-negative. Let's then do the proof when we assume that A is negative, and in that case, the absolute value is negative A. In this case, we can prove this chain of inequalities, where, again, this is merely by reflexivity, and this, right, negative A under this assumption is going to be greater than 0, and so something greater than 0, and A we know is less than 0, so we're going to get this inequality. Okay. Again, reintroducing the absolute value. This time, A is the same as negative absolute value. This time, negative A is the same as regular absolute value, and we get the desired inequality yet again. So that concludes the proof for part 4. And we just have to prove part 5. Now, I think I'm noticing that here in my write-up, although I'm supposed to do an if and only if proof, I think I actually only did the if part. But maybe I'll just write up the only if, or sorry, I did the only if. I still need to do the if part, but I might just write that up rather than retype these solutions. So anyway, we're going to show that we're going to assume that 0 pre-seq epsilon and A minus B pre-seq epsilon. And under these conditions, we want to show that B minus epsilon pre-seq A pre-seq B plus epsilon. So, okay, we know from the result in part 3 that because we are dealing with an absolute value here, then we can say that the stuff on the inside of the absolute value is in the middle of this chain, right? With its negative absolute value on the left, and its positive absolute value on the right. So we get this chain of inequalities. But then we can talk about how absolute A minus B is smaller than epsilon. And so it is easy enough to show that, especially over on this end, if we replace that with epsilon, we get something bigger. So this inequality is justified. And on this side, the logic is similar, except with a negative sign. So we get something smaller than negative absolute A minus B. But in any case, so we get, right, so it's not too hard to justify these inequalities based on everything that's given so far. And at that point, you can just add B to everything and you get the desired result. We also wanted to show that you could get this. Well, let's backtrack to the point where we had negative epsilon pre-seq, what was it, A minus B pre-seq epsilon. Now this time, what we could do is subtract A from everything. And then we get this, right? So from here to there, subtracting A. Now we can multiply by -1 throughout. It flips the inequalities, but you get this as a result there. And we're done. So let's now talk about the other direction that got left out here, the if direction, where we would assume this time that this chain of inequalities holds, and then what we're trying to reach is going back to that inequality with the absolute value in it. Okay, so if we assume that B minus epsilon pre-seq A, pre-seq B plus epsilon, we can add B throughout, subtract B throughout, and we get that. And then from here, we can maybe take it by cases, again, considering, non-negative, positive, but, we'll make our cases based on what A minus B is. So suppose that A minus B is non-negative, right? So if A minus B is non-negative, then the absolute value of A minus B is equal to A minus B. And then what we get from this portion of the chain of inequalities is that absolute A minus B is A minus B is pre-seq epsilon. And that, right from here to there, that's what we wanted to prove. Okay, now let's consider the case where it is negative. So A minus B precedes 0. And in that case, the absolute value of A minus B is equal to B minus A, right? So let's go ahead and get B minus A into this picture somehow. Well, we could do that by multiplying throughout by -1. So if we take that and multiply throughout by -1, then we would get that epsilon negative, right? Because if you multiply by -1, this turns into negative epsilon, but flips to the other side because all the directions of the inequalities change. So multiplying throughout by -1, you get negative epsilon on the left, which kind of neat that that it ends up not actually changing the locations of the epsilon and the negative epsilon, but you get this. So anyway, that's what. And now this thing is equal to absolute A minus B. So yet again, we get that absolute A minus B this time is equal to B minus A, but that pre-seq epsilon, and that completes the proof. And I'd like to end the video with an invitation to ask questions. So if you found anything confusing in this video or in related portions of the textbook, then leave a comment with as clear a question as you can make it. And if I can address it in the comments, I will, but if it's involved enough, then I might make a video and include it in the playlist.